What can dark energy teach us about the hidden world of dark data? The mysteries of dark energy and the challenges of dark data, highlighting the parallels between cosmic expansion and data gaps. The universe has always intrigued scientists with its vastness and mystery. Decades ago, in the 1990s, physicists began measuring the brightness of certain supernovae in innovative ways. These observations reinforced conclusions dating back to 1929, when Edwin Hubble discovered that galaxies are moving away from each other. The growing distances between them hinted at forces far beyond what we can see, dark energy and dark matter. As these supernovae dimmed over time, the universe's expansion became undeniable. This phenomenon could have been inferred even earlier. Albert Einstein's equations of general relativity in 1917 suggested a dynamic, expanding universe. However, Einstein hesitated to accept this conclusion. Today, the leading explanation for this cosmic behavior comes from the lambda cold dark matter, lambda CDM, model. According to this framework, dark energy accounts for 68% of the universe's mass energy, while 27% comes from dark matter. The remaining 5% comprises the normal matter we encounter daily. The precise workings of dark energy remain elusive. One intriguing hypothesis is quintessence, a proposed fifth force of nature. This theory suggests that the universe's expansion or contraction depends on the era of observation. Around 10 billion years ago, this force may have turned repulsive, driving galaxies apart. In the distant past or future, it could behave attractively instead. Other theories, often popularized in science fiction, speculate about time warps or distortions in how we perceive and calculate cosmic phenomena. Despite these mysteries, most scientists agree that the universe is expanding at an accelerating rate, consistent with Hubble's observations. This expansion not only confirms the dynamic nature of the cosmos but also paints a picture of a universe growing darker over time. The analogy between dark energy and the challenges humanity faces in managing information is striking. Dark data, an unseen obstacle. In 1997, Dame Frances Cairncross's book The Death of Distance examined how the communications revolution was shrinking the world. Advances in the internet, computing, and networking have undeniably made the globe feel more connected. Yet, the digital age still falls short of answering humanity's most pressing questions. More critically, it struggles to help us identify the best questions to ask. The exponential growth of data hasn't solved this problem. Instead, it highlights an uncomfortable truth: many questions requiring data retrieval, integration, and analysis remain unanswered. Often, the right data exists but fails to deliver actionable insights. This dark data, unconnected, underutilized, or poorly contextualized, remains an untapped resource. Without proper context, this data lacks precision and fails to illuminate problems or solutions. Dark data parallels the concept of dark energy in its obscurity and potential. Both represent phenomena that could yield transformative understanding yet remain beyond our grasp. In the case of dark data, the challenge lies in reducing the data distance between information and those who need it most. Bridging the data gap. Data distance refers to the gap between key consumers of information and the data required to solve their problems. Enterprises frequently make assumptions that widen this gap, such as underestimating the value of integrating heterogeneous data sources. Structured and unstructured data, as well as internal and external sources, must be melded to derive meaningful insights. Semantic graphs provide a powerful solution to this challenge. By integrating diverse data at scale, semantic graphs create a cohesive framework for knowledge. These graphs unify disparate information, allowing organizations to uncover patterns and connections that would otherwise remain hidden. Real-world examples illustrate the potential of reducing data distance. Diffbot, a company specializing in web crawling, uses these techniques to deliver valuable e-commerce insights. Since 2016, Montefiore Health has leveraged its knowledge graph to gain personalized insights for patient care. These achievements demonstrate that enterprise-scale knowledge and data management are not just possible but transformative. Toward a unified data approach. Despite advancements, many organizations remain unaware of the potential to unify knowledge, content, and data management through standardized techniques. Often, separate departments handle these tasks, leading to inefficiencies and missed opportunities. A single, integrated approach can streamline processes and make data more accessible to end users. Unifying data management enables the creation of shareable, contextualized insights. This clarity can illuminate complex problems, much like how reducing dark data could help address humanity's most urgent questions. Just as astronomers strive to understand dark energy, technologists must harness the potential of dark data to shed light on the unknown. The universe, with its accelerating expansion and growing darkness, serves as a profound metaphor for the challenges we face with information. Both compel us to look deeper, question assumptions, and push the boundaries of understanding. By bridging the gaps in knowledge, whether cosmic or data-driven, we can illuminate paths to discovery and progress. Dark energy, a term coined to describe the enigmatic force driving the accelerated expansion of the universe, continues to be a major mystery in modern physics. Its discovery in the late 20th century revolutionized our understanding of cosmology, but much about its true nature remains speculative. Here, we can delve deeper into what we currently know and explore new ideas regarding dark energy that could offer further insights into its fundamental properties. Nature of dark energy. The current understanding dark energy is understood to make up about 68% of the total energy content of the universe, playing a crucial role in its accelerated expansion. This mysterious energy is thought to act as a sort of anti-gravity, pushing galaxies away from each other rather than pulling them together as gravity does. It was first suggested by observations of distant supernovae in 1998, which revealed that these stars were dimming at a rate faster than expected, implying that the universe's expansion was speeding up rather than slowing down, as was previously thought. The most widely accepted explanation for dark energy within the scientific community is based on Albert Einstein's cosmological constant, a term he initially introduced into his equations of general relativity to maintain a static universe. However, after the discovery of cosmic expansion, Einstein discarded it, calling it his biggest blunder. In modern cosmology, the cosmological constant, denoted as lambda, is revived as a plausible explanation for dark energy, although there are alternative hypotheses. Theories of dark energy beyond the cosmological constant. 1. Quintessence. While the cosmological constant implies that dark energy has a constant energy density across time and space, quintessence presents a dynamic theory where dark energy's properties change over time. 1. Quintessence suggests that dark energy is not a constant but instead varies with the expansion of the universe. 1. It is represented by a scalar field, much like the fields that govern other fundamental forces. 1. Depending on the nature of this field, it could behave differently in various epochs of the universe's history, potentially even reversing the expansion in the far future. 2. Modified gravity theories. Another set of theories posits that what we are observing as dark energy may actually be a manifestation of modified laws of gravity at cosmological scales. 2. These modifications arise in an attempt to account for the accelerating expansion without invoking dark energy as a separate component of the universe. 2. These theories include models like F or gravity, which alters Einstein's general relativity to allow for an accelerated expansion without the need for dark energy. 3. Extra dimensions. Some speculative models suggest that dark energy could be the result of extra spatial dimensions beyond the familiar three-dimensional space we experience. 3. These dimensions could influence the behavior of gravity and result in the observed accelerated expansion. 3. Theories like string theory propose higher dimensional spaces, which could potentially give rise to effects resembling dark energy. Observational evidence and challenges. Despite the fact that dark energy is responsible for much of the universe's observed expansion, its effects are subtle and only detectable on cosmological scales. Astronomical surveys like the Sloan Digital Sky Survey and the Dark Energy Survey aim to map large regions of the universe and measure the cosmic expansion over time. Such observations focus on distant supernovae, the cosmic microwave background, and large-scale structure surveys to map the acceleration of expansion. The challenge lies in the fact that dark energy is not directly observable in the same way that galaxies, stars, and matter are. We cannot observe it in isolation or measure it directly. Instead, its existence is inferred from the behavior of objects on cosmic scales. Understanding dark energy requires increasingly refined measurements, sophisticated mathematical models, and advances in both observational techniques and theoretical physics. Dark energy's role in the fate of the universe. One of the most intriguing implications of dark energy is its potential to influence the ultimate fate of the universe. If the current rate of expansion continues unchecked, some theories predict a scenario known as the Big Freeze. This would entail the universe expanding indefinitely, with galaxies moving further apart and eventually leaving isolated stars and black holes in an ever-cold, dark cosmos. Alternatively, Some models involving dark energy suggest the possibility of a big rip, in which the expansion accelerates to the point where the fabric of spacetime itself tears apart, ultimately destroying galaxies, stars, planets, and even atoms. Though such scenarios seem distant, they offer profound insight into how the universe could evolve over unimaginable time scales. Bridging the gap in knowledge, parallels with dark data. The concept of dark energy shares an interesting parallel with dark data, an emerging challenge in the realm of information science. Both represent phenomena that exist but are largely hidden from view or difficult to understand in full. While dark energy could potentially transform our understanding of the universe, dark data has the potential to transform industries, organizations, and decision-making. Just as cosmologists use advanced techniques to measure and infer the properties of dark energy, data scientists must develop new methodologies to extract value from dark data, unstructured, untagged, or underutilized information lurking within vast datasets. As dark energy remains one of the biggest unsolved puzzles in physics, dark data represents a vast untapped resource that requires careful management, contextualization, and integration. With the right tools and technologies, both dark energy and dark data offer the potential for groundbreaking discoveries, whether in understanding the cosmos or solving real-world problems.